you all to fill out the feedback forms because the Turing Gateway, like all of us, like big data, so we want to process your data from the day. So after filling out the forms, you can leave them at the reception desk. All right, so welcome to the last session of the day. So our first speaker is Dave Yearling from British Telecom, and he'll talk to us about big data challenges in large IP.
Well read. Right. Okay. I'll be sucking a sweet, so please forgive the slurping noises, but I've got a sore throat. So I work in the data science research group at BT Research Labs, and what we try and do is support the rest of the organisation in all things data science, trying to exploit all the best techniques that we can find out there in the big bad world to the problems that the business face. Today I've seen lots of different examples. I'm only going to talk about one example where we're using some feature extraction techniques to be able to feed into some sort of probabilistic model so that we can actually then produce alarms that inform network operations who manage these large IP networks in the estate that help everybody in the UK get broadband. Okay. There we go. Okay, so in trying to explain where the hell these IP networks sit, and if I can get the pointer working. So basically our customers are sat here and here, because there's lots of customers, and they're connected by various ways to exchanges, by either fibre or copper or aluminium in some cases, or they get connected by their mobile provider, and they get then all into an exchange, which is then a nice big pipe into this IP network. That's the core network then that takes all that information from customers and transmits it across the UK to some machine somewhere on the edge of the network where it goes into the internet and the rest of the world. That's basically what it does. And so you imagine there's lots of customers here, all wanting one thing, all wanting fast data connections, all wanting reliable data connections, and if they don't get it, we get into trouble as a business. So the key thing here is this set of routers called edge routers, and all they are is just basically really powerful large computers that take in Ethernet traffic from the customers, pass it all up into IP traffic, and send it on its way through the network, going through several routes, several other machines, until it gets to their content provider, the internet or TV, whatever they're wanting to consume in terms of their data. So we've got about 1,000 of those edge routers, of those computers, and that sits in a network, a big core network, about 3,500 routers, which is the whole estate. But we're going to concentrate just on one type of router, because it's nice and uniform. It's one provider, one type of machine, no variance in terms of the kit that's inside it. And what we're trying to do is actually predict when things go wrong on those devices, and in particular when they go wrong on the bits inside, which are the line cards. And each router roughly has about 10 line cards, 10 slots, and each one of those line cards has about 40 ports on it, give or take. And those condensed ports are then piped across the network onto other machines, and they're connected in all sorts of manifold ways, so there's lots of resilience in that network so that they can actually get the data that they need. Now that's all well and good, but how do we manage that network? Just like, because Andrew was talking about the power network, this is highly sort of difficult stuff. If it goes wrong, it has big impacts. One fault on a router can knock out many thousand customers, and then we get into trouble. So we're trying to really predict when those things go wrong, when cards go wrong. Can we actually, rather than let them go wrong, get in there quick and tell operations it's going wrong, and actually use big data to help predict that. So they use currently performance metrics. There's about 12 metrics on average on every port. And that means that they had to look at, just for those edge routers, about 5 million time series constantly, monitoring it every 15 minutes. They don't do that. They have sets of machines that try and pick out patterns, not very successfully. And you can see there's quite a lot of observations every day. So we're trying to say, well, actually, can we do something with those metrics that are better than they currently got with this sort of machine, very simple alarming methods that they use at the moment. Those metrics are used often by operations, and they actually use those in a retrospective way. A fault comes in, a line card goes down, and they don't know where it is. Typically, they get the fact that something's gone wrong. They have to go and find where that thing is in the network. And as you can imagine, there's 10,000 of them to look at. It's very difficult to know which customer is affected on which card at any one time. It's not a simple process, so it's used in diagnostics. So if we want to predict, it makes sense. If they're using this in the hindsight way, well, surely we should be able to use the same sort of data inputs to maybe predict. Because why would we wait until the event happened if there's a pattern in the data currently that they're using to detect that there's a problem in this particular line card? Why don't we use that proactively rather than wait for it to happen? So that's the idea. And we can't predict everything. Power outages, they're force majeure. We can't do anything about that at all. It's just one of those things. But what we can do is actually take those metrics and react to them. Because we want to react to them with a good lead time. We want to be able to give ourselves time to, rather than 15 minutes, which is no way we can actually plan any engineering work. We'd like to put some time into the mix where we can actually plan some overnight work to maybe replace a card offline so that the customers don't even know there's anything going wrong. They get a very low impact on their service. So we summarize the metrics hourly, and then we're trying to extract those features in that time series. So a time series like that, we want to say, well, what's going on? What's strange about that time series? That is a predictor, or something that can go into a predictor to a line card fault further on down the line. So that's what we're trying to do, and we'll talk about one of the techniques. We've got lots of techniques. We'll just talk about one of them, and that's the cortical learning algorithm. And of course, because of the way this huge amount of data that's coming through, it has to be deployed on a big data platform. But the problems that we have are literally, it sounds very simple at the moment, there must be something really obvious here about what's going wrong with those time series on those metrics to indicate that there's going to be a problem down the line. The trouble is it's not, it's quite as simple as that, because all of those time series are hugely heterogeneous. They should be nice and cyclical, they should be nice and seasonal, but they're not, because the actual routers themselves, as part of their normal behavior, will move things around, shift things around. So you get drops naturally in the normal operating process of the router. So they're very, very difficult to model. So they're very heterogeneous, there's lots of them, so we need something that can run across the whole thing and be quite simple to operate. So the other thing, it has to really operate in a streaming sense, because the operational element of the national management network, they only see things in a 7-day window. They don't keep any data after that. And that's not enough to do any reasonable time series analysis. So we have to have something that we can implement that's really light and handle stream data like a Kafka service, something like that. So we can actually just take the observations in, score them, or whatever we want to do, and get them out for action. On an hourly basis, not necessarily 15 minutes. The other problem sits within how they fail. A card can fail for a multitude of reasons, whether it's a chip, whether it's a memory issue, whether it's a heat issue, where there's all sorts of different reasons why a card could fail, and each one will have a different presence in those metrics up here. So they're not going to be, there's not just one failure, there's a family of failures that we have to try and predict. So that means we have a family of models, so lots of models, and also they're quite rare. So we have about 10,000 edge routers there that we're modeling, and roughly up until Christmas, the financial year, we saw roughly in the region of 300 total card faults, outages, so they affected customers. So that's great. It's very rare, which is not as near as, not as 99.999% reliability, but it's it is quite rare. So it's quite a difficult thing to model in terms of how we actually build the models in the first place. It's a big problem. And also, because of these interventions will cost money, we want nice, low false positive rates when we go to deploy that in the field. Okay, so why is this so important? Well, we all know that our own personal needs for data are huge. Everybody here is connected at the moment, and you expect to be connected. You expect to get data on demand. You expect to go home tonight, watch whatever you want on demand, I would assume, and soon you'll want it always available in 4K, and soon you'll want your family and friends in the building to do the same thing. So the demand for data is just growing exponentially. It's getting bigger and bigger and bigger. And also, we've got the increase of the mobile. Mobile is becoming the de facto interface with the internet. So it's going to get even bigger, especially with 5G coming along in 5-10 years' time. Become more prevalent. So 4G, obviously BT's got a big stake in that now with the EE. So 4G is a really important pull on this. We serve the 4G Ethernet traffic in the same way through this network. So we want to support that as well. All of them wanting fast, reliable data services. And if we get it wrong, we get an outage, we get things like that, which unfortunately was a long time ago, not that long ago, 2016, but you know, not yesterday, where we lost several hundred thousand customers in one evening with one router going down. So one router went down of all those 3,500. We lose that number of customers. You know, it's not as serious as power lines, but certainly we get in the press, and it affects the share price, and of course the customers. So we just don't want it to happen. We want to get ahead of the curve. So what do we do now as a business to actually sort of remedy this? Well, it's very simple. Because there's so much data coming in, they don't know what to do with it. They certainly can't monitor those, you know, billions of records. They just don't know what to do with it. It gets stored in a big data warehouse that they can query individual elements. They can't really do any bulk analysis on that. It's not structured that way. So what they do instead is just apply some simple thresholds. And there's nothing wrong with that. Certainly for essential things like temperature, well, we wouldn't do anything else. If the temperature reaches a certain degree that's unacceptable for a processor to work, you call in the cavalry, you fix it. You get in the air conditioning, you do something about it. So that's obvious. We can't do away with those sort of simple, straightforward gauges. But most of them are either too complex, not even understood. Certainly some of the chip errors that get reported off these, because obviously these things are really quite complicated. The errors that get reported from the vendors don't mean anything, and typically we get loads of them coming through. So of a day you'll just get thousands and thousands and thousands every hour just coming through the door, so they ignore them. So typically alarms get ignored. So you know, it's just not useful information. Lots of information, but not particularly useful, because they can't act upon it. They can use it in retrospect again to find out what's going wrong, but it's all in hindsight. It's not actually what it's designed to be, and that's proactive. And of course you don't get anything, you don't get close but no cigar, you don't get any data recorded. So anything approaching a threshold doesn't get recorded, it gets thrown away. So we only get those we call them smart alarms. We're not particularly smart. So what they're currently trialling in the rest of the business, there's a part of the business that's doing this at the moment, which is quite interesting. They're doing fast reactive logic. So, okay, it's not predictive in the sense that it happens after the event, but what they're doing is using customers' behavior. And when I mean customers here, I mean, you know, big content providers, you know, Skies and TalkTalks, people like that who are using our network and are worried about a certain service that are coming through. So they actually do some tests to find out what's going on with this particular stream. So they'll do some tests on the network, and we obviously hope we own the tests for those particular companies, because they're our service on the demand testing. So we can just simply triangulate those tests. And so actually there's a hotspot in the network. This router's going down, this line card in that router's going hot. We can then talk to the customers directly. We know what's going on. We can see it already. We're on the case. We're going to replace the card immediately and tell your customers, not to worry, we'll be back online shortly. So it actually gives us the next best action, and it's certainly faster than waiting for the ticket to arrive through the door. So what we're trying to do is something a step beyond that and actually do timely predictive logic. So imagine, rather than waiting for all this to happen, we had a system that we could monitor those metrics and say, actually, in 5 days' time, say, there's going to be a problem on this spine card. It's looking dodgy, so you may want to look at doing something about it. You may want to plan some engineering work. 5-day windows, I'm using that as a complete heuristic. May not be 5 days, it might be 3. Depends on what we eventually come up with. But at least days, not the hour, not the same day, but actually at least a day, so they can actually plan cheap plan maintenance to get in there and fix it without having a call out, without having people running around trying to find source cards quickly. So that's the aim. We're not there yet. This is just the journey through, and this is the roadmap for that journey. So we take each of those machines, these computers, and they've all got cards, they've all got ports, they've all got metrics. Those metrics we're sort of capturing, and of course this is in a sort of a high-level view. The process, we want to clean that up. 15 minutes at the moment. They're actually moving to 5 minutes, but we want to work on an hourly basis because sometimes we have missing values. We don't get the full 15 minutes going through the hour, so we actually take the means for the hour. So we clean that up. If we're actually doing some of the statistical techniques that I'll mention in a second, we also have to make that stationary because you'll see in a second some of these time series, they are very seasonal, as you'd expect. So we need to make sure they're stationary and then make sure that they're homogeneous, and we make sure that they're as Gaussian as possible, so that they work with some of the techniques on the stat side. But the technique I'll talk about doesn't rely upon that, so that's good. And then we actually put it to the next stage of the process, and that's that we try and do some feature extraction. This is the anomaly detection. So we're saying, well, actually, are there any strange, I don't want to get this completely right, all I want to do is actually pick out things in the time series that are actually weird or strange, because that's exactly what the engineers in the operation platforms do. They just look at it and think, oh, of course that's something that doesn't look right. They don't do any analysis, they just look at it visually. So if we could do that automatically, that's what we're trying to do. So that immediately reduces the data. They're going into the next step, we reduce that. And then obviously we can use those data points to help the operations further. They can use them for diagnostics and other things that help them plan other works or other points of intervention that they might want to work upon. So prior to the prediction point, we wrap a heuristic around it, and that's a simple heuristic where we just, at every time t, we take a window back in time and we sum weight all the anomalies that we saw in that period. So we just say 15 days, I'll show you in a second. Take 15 days, sum weight all those anomalies, if there are any, and then let's report that figure. That gives us the black line. And then for any point in that black line, any time t, we know the state of that time series in terms of its anomalous nature. That's all we're doing. And then we put it through we're putting it through Bayesian network models, and we're putting it through some sort of gradient boosting to try and predict, give us some probability of a card failure happening further down. So when we've built those probabilities, well, what we'd like to do, we haven't done it yet, is to actually record them all the time. Just keep recording those probabilities. So we get a trend of probabilities for every device, for every router on the network. So you can see these probabilities over time. And then we can use them to say, well, actually, this particular machine's hot, this computer over here is hot, and more than that, we can say, well, these are trending. These are getting worse. These are actually exhibiting the same sort of signs, and actually, because they're connected, there's some degree of impact that you experience on these routers because this one's going pear-shaped. So we have a bit more of a topology view of what's going on with the probabilities. The challenge is, we are obviously we don't want to be windowing in real time because we've got 7 days typically in the operations to work with. We'd rather not window, so we have to get over that for some of the techniques that we're using for the feature extraction. So currently I'm concentrating on this top one here, the cortical learning algorithm, but some of our colleagues in Lancaster have developed some great algorithms that work pretty fast, enable us to use some statistical techniques, but they rely upon a time series. We need the whole time series to go through the machine every time we want to check anomalies. So running these things in real time is difficult, not straightforward, obviously, and we are not anywhere near real time yet. But that's more to do with the fact that I can't move the code close to where the data sits. So we have an issue there in terms of operations, really, rather than a technical issue. And also as a business, even though we're in the research area, we're not experts in any of these techniques at all. We're not interested. We're not experts in any of the mathematics or statistics that underlie them, and we don't know that we want them as rigorous as possible. So by working with some PhD students in Lancaster, we get that benefit of getting them top-notch and getting into some really quite interesting solutions for multivariate problems, because this is a multivariate problem. We're not tackling it that way, but it is a multivariate problem. And they also have interesting things to do in getting missing values sorted out. So the input into this heuristic, we've got, it's only a heuristic, and it's a very simple one that needs work. But once we've done it once, we've done it for all the models that we're going to predict. The rare events mean that we have to do some sort of thought experiments to build models. It's not really quite clean. There's lots of other noise going on. So we have to try and clean the data a lot in order to produce the models. And also the change in probabilities make a nice overlap in our decision process in order to say, actually, this card's going to go pear-shaped. Okay. And of course, I've just mentioned already, getting it into the business isn't straightforward. So what do these time series look like? And these are just two metrics. So there's two metrics recorded on three cards, three ports, sorry, on the same card that failed, and that failed at that point there, the black dotted line at each parts of the graph, and each graph goes back 20 days. You can see on some of them, they're nice sort of regular behaviour on a week basis. They all behave very similar, although not quite exactly the same. Apart from that one, it's the same metric, it's the same device, but behaving in a totally different way. And that's the sort of thing you see all the time. They're basically, by virtue of the router's logic, it's doing something different. It's doing something completely different. So it's very difficult to handle these variations of time series. And any one of those time series could go into that particular mode at any one time and not be a problem. It's perfectly normal. But we don't know when that's going to happen, and we can't know when it has happened. The same for this particular metric. You see different patterns again. They're totally different. Every one of those is different. They're not the same at all. But what the interesting thing is, all of them exhibit strangeness close to the point of failure. So they're all exhibiting absolute declines here, or peaks here, for example, or some sort of weird step change there. Here, we've got this increase in frequency and amplitude. All sorts of strange things are going on in those time series prior to that point of failure. So obviously, what we're trying to do intuitively kind of makes sense. So what the engineers themselves, if we could mimic those engineers, yeah, we could get an algorithm that does exactly the same as that, then we'd be onto a kind of a good thing. And that's what we're trying to do with the cortical learning algorithm. And I won't go into massive detail because I don't know it. So basically, it tries to model, it tries to behave on the principles of the neocortex, which are, basically all the higher functions of the brain are contained within that neocortex, mostly. They obviously communicate with regions deeper in the brain. And they basically, the key thing to it all is that we're looking to simplify the inputs that are coming in. All inputs, whether they're visual or oral, or whatever they might be, touch, they all get converted into the same sorts of data signals in the brain. They're not different, they're the same. And that's why you get problems in terms of synesthesia, and also when you get plasticity helping people recovering from strokes. So that's a good thing. And they do that by actually storing those signals in an invariant way, not an exhaustive way. So basically we capture the elements, the actual basic information, and we fill in the rest. So for example, we all know what a chair would look like as an object. We don't have to know all possible variations of a chair. We just don't have the need to have lots of exemplars. We just know what a chair would look like. That's the sort of the invariant principle. So it's robust against noise, which is really cool. That's what we want. And also the brain tends to want to be able to predict sequences. So we're always wanting to, what happens next? So when you throw a ball, You don't solve any partial differential equations, or you just catch the ball, because you're always anticipating, you're always solving pattern problems. That's all you're doing. When you're listening to music, you're doing the same thing. You're anticipating all the time what will happen next. And that forms the basis or the principle of the CLA. All it's interested in is, do I recognize this? Can I predict what happens next? That's all it does, every time. So it's a great thing for us, because it's kind of what we do. It's a bit like the brain. So, and the great thing is it self-learns. So you just give it one variable at a time, or one observation, sorry, at a time, and it'll take it. Do I recognize this? Well, it starts off saying no, but it starts to learn. It starts to learn as it goes forward, and which is really good. So we just literally, all we have to do is put that model right next to the data stream and say, just look after that. And it'll keep on observing the data and then reporting back what it sees, which is great. So we can use it on streaming data, and it seems to be a very advantageous thing to do. Great. Problem is, it's not particularly easy to use necessarily, in the sense that it's very hard to tune. There's about 30 parameters. I'm going to make that number up, it's about 29, but 30 parameters that you may wish to fiddle with in order to get this thing to work tip top. So it works out of the box, but not massively brilliant. So this is a crash course in what it does. So basically, like the layers of the brain, the brain's typically has 6 layers, something. And basically that tries to replicate that with these columns. And each column has lots of cells in it, which are sort of distally connected to other columns. Okay, and this is the part where it learns the sequences. And each one of those columns in turn is mapped to the input. And that input is this big, long binary vector. They're all statically set up that way. When you initialize the model, you just literally map them. All columns are used, and they all map to that vector. And that vector is just literally the representation of the observation. The observation comes in, it gets encoded by one of the clever encoders, which turns that observation into a series of zeros and ones, with 2,000 zeros and ones. But only 2%, 40 of them, are actually set to 1. So it's sparse. And the reason why that's sparse and why it's useful is that invariant property that we're looking for. So basically, the chances of you having a dissimilar observation coming in and mapping the same region and the same ones is very low because of the way it's set up. So obviously, similar observations must map to similar binary vectors. That's the way the encoder works. And we don't have to store 2K, we just store the 40 bits that we're interested in terms of their indices. Then it goes through a recognition bit. So we take it through the spatial pooler, and all that's about, and we'll go through the details, it jiggers around with these things in order to recognize the observation. Do we recognize it? Have we seen it before? Which one does it fit? And once we've done that, we go through the prediction phase. So okay, we've seen that observation. Can we tell the user what's going to happen next? What's going to happen next? Where's that ball going to be? Where are we going to go to next? What's the next word? What's the next tune in the song? And that's what that temporal pooler does, and that's where it learns, builds these synapses, these mimicked synapses. But what we're interested in is the next stage of the process, where we perform the anomaly calculation, which is really straightforward. All we do is say, well, we've got an observation. How well did we predict it last time? By looking at the temporal pooler at t-1, we compare it with the spatial pooler at t, and the difference in terms of a proportion of correctly matched. That's a bit erratic. It tends to jump around a lot. It's not particularly useful on its own, but what we can do is kind of smooth it with a moving average. So we take a short-term window and average over that window, compare it to a long-term window, and saying, is this kind of weirder than that window? That's all it does. And by virtue of simple statistics that even I can do, well, we end up just calculating the tail probability, and away we go. We get the likelihood.
Can I ask a question?
Yeah.
So it sounds like you're describing a recurrent neural network. And is this a recurrent neural network, or is it doing something slightly different?
I think it's doing something slightly different. I don't know much about recurrent neural networks. I think if you read Jeff Hawkins, he kind of rails against that sort of thing. It's not quite the same, but I don't know the finer points of detail.
So is this in the literature? I mean, is it this?
Yeah, if you look, I hope I included the. Yeah. Okay, so if you look at this is all available software. I've not written any of this. This is all available. Okay, so this is all. Numenta is the organisation. Jeff Hawkins is but it's not. The CLA is not necessarily. It's his baby, but it's a general. There's lots of other versions of CLA. It's not just him, but that's the one we use. But it's not quite a neural network. There's some similarities by virtue of it's trying to model the same thing.
Well, I suppose my next question would be, have you compared it with a neural network? Conventional methods should be using RNN.
Yeah. I haven't done that because I think that I'm not quite sure how it would work as we roll it out. How would that work? I don't know. You have to tell me. Okay, so we end up with a probability, which is nice, and then we can carry on with the game. So what does this look like in practice? We do a thought experiment here, and we just take a whole load of card failing time series, and we take a whole load of controls, and we compare them together to see what happens when we run the CLA across it. And we see, for example, when we talk about the control, the yes cohort, the card failures, what we do there, because we want to predict well in advance, for all those card failing time series, we take the card outage and we go back 5 days. And so actually the point of measurement we're going to take for this experiment is 5 days before the failure. For the controls, we'll take a time series that gives us enough time series to be comparable with the yes cohort, and we'll say that we'll measure it at that point, random. Okay? And then the heuristic is, again, I've mentioned, just a 15-day rolling window up to the point of observation. Anything out before that is discarded, and we sum weight within that window. So when we run the CLA across just this time series to see what it looks like, we see a crowd of anomalies being created at the point of anomaly. We observe at the X, of course, and we sum across the window, and that's it. So it looks like, for this case, it looks like it's thrown something. Whether it's meaningful or not, we don't know, but it just shows something's going on. And of course, after the card outage, the thing's going crazy anyway. So there's no monitoring after that. If we look at the populations of these cohorts, and what do they look like? Really, they look encouraging rather than definitive. So basically, we are seeing a difference in distribution. So with that simple heuristic, we do see a difference. Whether it's worth going at is of course moot, because we're getting far too many false positives. Even just visually, you can see this will be no good for prediction because of all the the no's up in the top of the distribution. But it's encouraging because most of the no's are of a median of 0, and the rest of them for the yeses are certainly bigger than that. So it's encouraging from what we can see in the data that we could use this sort of technique, but we probably have to use do some more work on the heuristics. The one I'm toying with is just maybe perhaps what we do is rather than just using that window, compare it to other windows, saying actually this is just like any other window. You take any other window in this time series, you're going to get the same result. This time series isn't really predictable. It's not going to give you anything. It's just too chaotic. So that would probably help. That would probably reduce the false positives. Also probably take out some of the yeses. But we also need to actually be more specific in what a failure is before we come to predict it. Okay? So it's encouraging. Yeah. So that's where we are with that at the moment. So I say it's not a done deal. We've still got to be able to build the models, and the models aren't really giving us what we kind of want at the moment. But in terms of the big data challenges, even though the CLA has promised, and it deals with streaming, so we can actually put it right on the time series and record and get those scores. It's not currently developed. The code I've written is in real time. It takes one observation at a time, but it's not designed to be run as a singleton model in a real-time environment. So that needs to be worked upon. The anomaly flagging isn't consistent. It can be, because it's self-learning. It self-learns. It will adapt. So sometimes it doesn't adapt fast enough in order to pick up other anomalies further down the line. That needs to be changed. And again, I've talked about the parameter tuning. That needs to be developed as well. The other ensemble methods, they're faster. They're simpler. They're faster. but we do need that window. So that's something we're trying to get to grips with. And yeah, so there we are. So it's more pre-processing, more standardization, trying to make it as normal and as Gaussian as possible for those type of methods. And really then we're just basically fighting against the business in terms of getting it out there and working with the operational guys, which is not an easy thing because of the way we're structured with our multi-tenanted Hadoop environment. So I think I'm running over here.
Okay, well, thank
Yeah.
you. And I was told that you're supposed to catch a cab right now.
Yeah. That's why. That's
So
why
if
I
you have
thought I'd
questions
skip
for
them.
Dave, email him because his taxi is waiting for him.
Thank you.
All right, so our next speaker